In this video, we will learn about polynomial functions and complex zeros. This is AP Precalculus topic 1.5. If you appreciate the content, please don't forget to hit that like button. Here's the formal definition of zeros of a polynomial function. Given a polynomial function p of x, if p at a equals 0, then a is a 0 or a root of p of x. If a is a real number, then x equals a is a 0 of p. Then x minus a is called a linear factor of p. Consider the function f of x equals x squared minus 5x plus 4. Because the degree is 2, we know this function has at most 2 real zeros, which will be at the x-intercepts of this function. We can find those zeros, also called roots, by factoring this function. F of x can be written as x squared can factor as x times x. 4 can either factor as 2 times 2 or 1 times 4. Looking at the 5 in the middle, I'm guessing that this time it's going to turn out to be 1 times 4. Inner plus outer must equal middle. Inner, I mean the 1x. Outer, I mean the 4x. Inner plus outer must equal middle. We control the signs. If I let both signs be negative, that will give me the middle of negative 5. That means negative 1 and negative 4. That was a quick review on factoring. Anyways, the zeros of the function are the values of x that will cause f of x to equal 0. So using the zero product property, I can set each one of these factors equal to 0 and solve. And that tells me that the zeros of the function are x equals 1 and x equals 4. So graphically, I'm going to have a 0 here and a 0 here. And f of x might look something like this. Zeros that show up on the x-axis like this are called real zeros. They're the ones that you get when you solve for x and you get x equals a real number. But consider function g of x equals x squared plus 4. This is not factorable. I can still set g of x equal to 0 and solve, but I would have to set the entire function equal to 0 since it's unfactorable. And then I would subtract 4 from both sides, so I would get x squared equals negative 4. And then I would take the square root of both sides. Don't forget, when you take the square root of a negative number, it's going to be imaginary. Also, I have to have a plus or minus here. It's going to be 2 zeros. And the square root of negative 1 is I, which stands for imaginary. So the square root of negative 4 is going to be 2i. So this is plus or minus 2i. These imaginary zeros will not show up on a graph. So the graph is going to look something like this, and it does not have any x-intercepts. Complex zeros include zeros like 2i and negative 2i that have imaginary numbers. But complex zeros also include the ordinary zeros, the real zeros, like x equals 1 and x equals 4 from the previous example. We will learn more about complex zeros later in the lesson. First, we need to talk about repeated zeros or multiplicity. If a linear factor x minus a is repeated n times, the corresponding zero of the polynomial has multiplicity n. Typically, we know that a graph of a polynomial passes through the zeros on the graph. However, when a zero has a multiplicity greater than 1, the graph will behave differently near the zero. This function, written here, is graphed to the right. Notice the behavior around the zeros of the function. The multiplicity of a zero is the exponent of its factor. So if we have a polynomial written in factored form like this, we can know the zeros by setting each factor equal to 0. So we get a 0 of x equals -4. This one has a multiplicity of 1 because the exponent is an invisible 1. We can include the multiplicity when we list the zeros. So when we say the next 0, x equals -1, we're going to say multiplicity 3 in parentheses. And then when we say x equals 3, we're going to say multiplicity 2. Notice what's happening at x equals 3 where the multiplicity is 2. You see how the graph bounces off the x-axis? We say that the graph of the polynomial is tangent to the x-axis. The graph of a polynomial will always be tangent to the x-axis at any 0 with even multiplicity. If a 0 has odd multiplicity like the other two zeros, the graph passes through the 0. Example 1. For each of the following polynomials, determine the degree of the polynomial, find all real zeros, and state the multiplicity for each 0. With the polynomial written in factored form like this, it's not immediately clear what the leading term would be, but we can find the leading term by focusing only on the highest degree term in each factor. So we've got negative 2x cubed from the first factor. From the second factor, it's just the x, ignore the 1. And from the third factor, we have the x, and don't forget that it is squared. So the leading term, I think I'll just put LT for leading term, would be negative 2x cubed times x squared. Therefore, the leading term would be negative 2, and then I'm counting up all these x's, 3, 4, 5, 6. So negative 2x to the 6th power. Therefore, the degree is 6. We can find the real zeros by setting each factor equal to 0 and solving. So from the first factor, if we set that equal to 0, we get x equals 0. If we set x plus 1 equal to 0, we get x equals -1. And if we set x minus 4 equal to 0, we're going to get x equals 4. 0 has multiplicity 3 because it's x to the third power. -1 has multiplicity 1. There is no visible exponent. And 4 has multiplicity 2 because we see the exponent of 2. For function g, we could find the leading term again by focusing on the highest degree term of each factor. So the leading term would be 3 times x squared times x to the 4th power. So that would be 3x to the 6th power, and the degree is 6. We do not get any real zeros from the factor of 3. There's no variable in there, so you can't set that equal to 0. If I were to set x squared minus 4 equal to 0 and solve, you could probably do this in your head, but we could solve this in two ways. This is a good review. We could either factor this, and this is the difference of two squares, so it factors as x plus 2 times x minus 2. That gives us two real zeros. X equals -2 from the first factor, and x equals +2 from the second factor. Each of these will have multiplicity of 1. Just as a review, here's another way we could have solved it. If I add 4 to both sides, I get x squared is equal to 4. then I could take the square root of both sides of this equation, and that would give me x equals plus or minus 2. Don't forget the plus or minus. But those are the two zeros that we found, positive 2 and negative 2. I have been skipping this step and doing it mentally, but I think I should mention it now. If I set x minus 2 to the fourth power equal to 0, the first thing I would do is I would take the fourth root of both sides of this equation. So that gets rid of the exponent of 4. So we just have x minus 2. And the fourth root of 0 is still 0. And then setting this equal to 0, adding 2 to both sides, we get x equals 2. So that's why when I look at a factor like this with an exponent of 4, I really just ignore the 4 and I imagine setting x minus 2 equal to 0, and I get x equals 2. What I'm not going to do is write down x equals 2 again, and then this x equals 2 would have a multiplicity of 4, but that's not how this works. So if we already had an x equals 2, and here's another x equals 2 multiplicity of 4, if we put those together, that's multiplicity 5. Just to explain that a little bit better, g of x is equal to 3 times, and then we factored this, remember, difference of two squares, so we could factor this as x plus 2 times x minus 2. I'm going to have to go off the page a little bit, but then we have the x minus 2 to the fourth power. But do you see that these factors are the same? We have an x minus 2, and then we have 4 more x minus 2's. So for that reason, g of x could be written like this: 3 times x plus 2 times x minus 2 to the fifth power. So that's another way to visualize why we are collecting these together and writing x equals 2 multiplicity 5. Side note, remember that the degree tells us the maximum number of zeros that a polynomial might have. If you count up the multiplicity and it equals the degree, you know you found all of the zeros. So here we have multiplicity 5, multiplicity 1, that's a total of 6. So that matches the degree. Look at part A, multiplicity 3 plus 1 plus 2, that's a total of 6. That matches the degree, so we did find them all. Part C, the main thing we need to do is factor completely. So looking at this first factor, this trinomial, I see that every term has at least one x in it. So the first thing I'm going to do is factor out that x. So that's going to leave behind x squared minus x minus 6. I think I'm going to change colors just so you can follow what I'm doing more easily. And then the trinomial x squared minus 7x plus 12. I think we can factor each of these trinomials further. So I'm going to go ahead and bring down the y equals and the x. But let's factor this first trinomial. X squared is x times x. 6. 6 can either factor as 2 times 3, or it can factor as 1 times 6. So I am going to try the 2 and the 3. In fact, I always think to myself, inner plus outer equals middle. I'll come back to that in a minute. But since the middle is negative 1x, the pair that is able to make a 1 by addition or subtraction is probably the one to start with. So I'm going to try the 2 and the 3. Inner plus outer equals middle. Inner is the 2x. Outer is the 3x. These have to add up to negative 1. I control the signs. It'll make -1 if I have a +2 and a -3. So that's a +2 and a -3, so there we factored it. So now I'm going to factor the orange trinomial. Again, the x squared will only factor as x times x. 12. 12 can either factor as 3 times 4, or 2 times 6, or 1 times 12. Since the middle term is -7, the 3 times 4 is the one to use. Okay, inner I have 3x, outer I have 4x. I'm trying to make -7, so both of these need to be negative. Also, -3 times -4 does make +12, so we factored it. Now, notice the repeated factor of x minus 3. So I can rewrite this polynomial as y equals x times x plus 2 times x minus 3 squared, there's your multiplicity, and then x minus 4. We can find the leading term of the polynomial by using only the leading term of each factor. So this will become x times x times x squared times another x. So that's 1, 2, 3, 4, 5 x's. That is x to the 5th power. That is the leading term. In this form, we can tell that the degree is going to be 5. The real zeros are x equals 0 from the first factor, x equals -2 from the second factor, x equals +3 from the third factor, and x equals +4 from the last factor. And here are the multiplicities of each zero based on the corresponding exponents. Notice that if I add up all of the multiplicities, I am getting the degree of 5. Complex roots. Some polynomials have roots that contain an imaginary number. We talked about this earlier in the video. This means that you will not see them on the graph. There will be no x-intercepts if the root or 0 is an imaginary number. The graph of f of x equals x squared plus 1 is shown to the right. To find the zeros of f of x, we would set x squared plus 1 equal to 0 and solve. This is just like what I showed you at the beginning of the video. Here's a key fact I need you to memorize. All imaginary roots come in pairs. If a plus bi is a root of f of x, then so is a minus bi. These are called conjugate pairs. Let's practice determining the conjugate of a complex number. This would be like 0 plus 4i, so the conjugate would be 0 minus 4i, and I'm just going to put -4i. Okay, this is like 0 minus I, so 0 plus I would be the conjugate, and I'm just going to put I. 2 minus 3i, the conjugate is 2 plus 3i. Alright, notice we only changed the imaginary part. So -4 plus 2i gives us a conjugate of -4 minus 2i. The real part doesn't change. This next fact is so important they call it the fundamental theorem of algebra. A polynomial of n degree has exactly n complex zeros when counting multiplicities. Remember that complex zeros, that includes real zeros and imaginary. Example 3. The graph of the polynomial function f of x is shown in the figure above. it is known that x equals negative I root 3 is a 0 of f. If f has degree n, what is the least possible value of n? Let's start by counting the zeros that we see. Remember, we are not going to see imaginary zeros, so those will be added on. So in other words, let's start with the real zeros, because those are the ones that show up in the graph. So the real zeros are x equals negative 1 and x equals 3. Now let's talk imaginary zeros. It is known that x equals I radical 3 is a 0. So let's write that down. X equals I radical 3. And we just learned that imaginary zeros come in conjugate pairs. So if 0 plus I radical 3 is a 0, then 0 minus I radical 3 is another one. So we have 4 zeros. But what about multiplicity? We are looking for the least possible value of n. So let's write down the least possible multiplicity. When the function is tangent to the x-axis, that means even multiplicity of that 0. So the smallest multiplicity possible for x equals negative 1 is multiplicity 2, because it has to be even. The function passes through the 0 of 3, so that could be multiplicity 1. Okay, it could be any odd number, but let's go ahead and just put 1 because we want the least possible. So, adding all of this up, we have 4 different zeros, but one of them is multiplicity 2, so including that, that's 5 zeros. So the least possible value of n is 5. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.